Hi folks, Chris McClure. We're now going to talk about rational functions. Now, in section 5.1 we talked about polynomials in general and how polynomials are combinations of power functions. Now, rational functions are basically fractions involving polynomials, where you have numerators and denominators involving fractions. So let's take a look here. Here's kind of the official definition, where you have a rational function given by big R of x is equal to this fraction of polynomials, where P and Q are polynomials. And this rational function is going to be defined for all values of x, just like polynomials are defined for all values of x, with the caveat that we will exclude the zeros of the denominator polynomial. So meaning where the denominator is going to be equal to 0, we'll exclude those values of x from the domain. All other real numbers will work as the domain. So when we talk about the domain of rational function, all we really need to do is just take a look at the denominator. Set the denominator equal to 0, solve for x. And this one is pretty simple, really. Just x plus 5 equals 0. That means x is equal to negative 5. So we'll exclude negative 5. And we could write the domain just like this using set builder notation. Okay. Here's another rational function, 1 over x squared minus 4. If you set x squared minus 4 equal to 0, solve for x, you got plus or minus 2. So we'll exclude those two numbers from the domain. Here's another example here, x cubed over x squared plus 1. Now, x squared plus 1 is never going to be 0 for any real numbers x. So the domain for this function is going to be the set of all real numbers. For this next function, for part D, hey, when x is equal to 1, the fraction has a 0 in the denominator, so we'll exclude 0. We'll exclude 1 from the denominator. So here's your domain. Any other real number will work. You can input any real number and you'll have your function be defined as long as x is not equal to 1 in this case. Now, even though you can, for this function from part D, even though you can factor the numerator and cancel a factor of x minus 1, and you have this equivalent function x plus 1, this function x squared minus 1 over x minus 1 is still undefined at x equals 1. For any other value of x, these two functions, the x squared minus 1 over x minus 1 and x plus 1, are exactly the same. The only difference between them is at x equals 1, where the little f of x is defined at x equals 1. But you have a hole at x equals 1 here for r of x, which you could plug by saying that, in a piecewise fashion, that this function r of x is going to be equal to 2 when x is equal to 1. In that case, you'd have a nice, well-behaved function, which would exactly be this one. But as it stands now, this function right here is not defined at x equals 1. Here we've got 1 over x squared. What does the graph look like for this function here? We know that at x equals 0, the function's not going to be defined. Let's use the table feature, which you can do on your calculator, to look at the behavior of the function as you get close to 0. When x gets closer and closer to 0, both from the positive sense and also from the negative sense, if you choose to look, the value of the function gets to be larger and larger. And if you were to plug in 1 millionth for x, then you'd have 1 over 10 to the 12th, which would be I'm sorry, you'd have 10 to the 12th power, which is an extremely large number. So the closer you get to 0, the larger that you get for the function. So what we say in mathematics is that we kind of take the limit as x approaches 0, and the function goes to positive infinity. Now, when you let x become large in magnitude, like as x gets beyond, your single digit numbers, for example, your function gets to be closer and closer to 0. So in the parlance of the higher levels of algebra and calculus and stuff, what we say is we take the limit as x goes to infinity, and the limit for the function is going to be 0. So there's two aspects that we really need to examine here. We've already taken a look at them briefly. The behavior of the function as x approaches 0 from the left and from the right, and you can see that the function is going to go straight to infinity and not be defined at 0. We oftentimes will say that the function blows up at 0. Any other value of x, the function will be defined for, but not at 0. Also, when x goes to negative infinity or positive infinity, the function is going to go to 0. You can kind of take a look and imagine that this curve will get closer and closer and closer to the x-axis. So what we say is that this horizontal x-axis acts as an asymptote, horizontal asymptote. And likewise, the y-axis, this vertical y-axis, acts as a vertical asymptote as x approaches 0. Let's talk about graphing function. Now we know what the graph of 1 over x squared is. So what is the graph of this function here? Well, just use transformations. If you replace x by x minus 2, then the graph will be shifted 2 units to the right. And then if you add 1 to the function, well, the graph is going to then be shifted up 1 unit, like you see here. So here's the graph of 1 over x minus 2 squared plus 1. Just by starting off with the basic function 1 over x squared and applying 2 transformations. So we talked earlier about asymptotes. Here's a kind of a closer look at what we were doing here. Take a look at this function here, 1 over x minus 2 squared plus 1. Now, when we take a look at what happens to the function when x becomes larger and larger and larger, you see that the value of the function gets closer and closer and closer to 1. And likewise, when x goes out toward negative infinity, the function gets closer and closer to 1. So we say that y equals 1 would be a horizontal asymptote. Likewise, when x gets closer and closer to 2, both from the left side and from the right side, you see that the function gets larger and larger and larger. So the line x equals 2 acts as a vertical asymptote. Those are kind of the idea behaviors of the function as x approaches 2 down here, or positive and negative infinity up here. So we like to use this notation here when we say that x goes to negative infinity or x goes to positive infinity. Where does the function go? What is the end behavior? And that end behavior of the function will tell you whether or not the function tends toward a finite value, and that finite value will be y equals that finite value. will be the value of y, as in the equation y equals that finite value. In this case, L is that finite value, and y equals L is that horizontal asymptote. So this is kind of what the graph looks like for that end behavior as x goes to infinity. And we'd say that the function approaches L. So y equals L would be the horizontal asymptote. Likewise, for the vertical asymptote, for the vertical asymptote as x approaches whatever this x value is, I guess it's c, then the function's going to go to positive or maybe negative infinity. We could have vertical asymptote where the function displays behavior like this, where maybe you let x approach a c from the left and the function goes to negative infinity, but if you let x approach c from the right, maybe the function goes to positive infinity. Or it could be that the function goes to negative infinity from either as x approaches the that value of c from either direction. So we'll come back to that slant asymptote. I skipped over something from the previous slide. Over here, this just shows that you could have your asymptote happen, your horizontal asymptote happen as you let x go to negative infinity. It very well could be that the function goes to negative infinity as x approaches positive infinity or something like that. But the end behavior for this function is that the function approaches L. That's what it shows there. So, it could be that y equals L for both as x approaches to the left or to the right of infinity, meaning negative infinity or positive infinity, both. Or one, or the other, or both. Okay. So we talked about these vertical asymptotes as well. And here's actually an oblique asymptote, where it could be that the function approaches infinity in the positive or negative sense, but along a line. I'll give you an example here pretty soon. So hold on just a sec.
I'll leave you, sorry.
Okay, I'm back. My wife popped in to ask me a question, so I'm back with you now. So we talked about these oblique asymptotes, sometimes called slant asymptotes, where the function approaches positive or negative infinity along a line. So I'll show you an example here in a minute. So let's talk about finding those vertical asymptotes. Actually, it turns out to be pretty simple, really. What you need to do first is take your rational function and factor out and cancel any common factors between the numerator and denominator. And then take a look at where the denominator is equal to 0. So here's an example of a nice reduced rational function. You see that there aren't any common factors. And then you set the denominator equal to 0, and you see that x is equal to negative 3. So at x equals negative 3, there will be that vertical asymptote for the graph of this function. Now, for h of x here, you see that this is a nice reduced fraction. There aren't any common factors for us to cancel. So you'll see a vertical asymptote at negative 2 and positive 2. Here's another example here. You got this function f of x is equal to x minus 1 over x squared plus 5x plus 4. Factor that denominator, and you'll have x plus 4 times x plus 1. And you set that equal to 0 and solve for x. You get negative 4 and negative 1. Those are your vertical asymptotes. Here's yet another example here. Now, factor the numerator, factor the denominator. Now, why do we only have x equals 2? Well, you know, in the denominator, you factor that, you get x minus 2 times x plus 2. But when you got the numerator, you got x plus 1 times x plus 2. So the x plus 2 factors will cancel, leaving you just with an x plus 1 over x minus 2. And that's why x equals 2 is the vertical asymptote for the graph of g of x. So I'll let you do this on your own on the graphing calculator. Go ahead and graph these 4 rational functions and see what you get. Compare the graphs and then comment about what the graphs look like. Here's what the graph of 1 over x minus 1 looks like. I've already done this. Here's what the graph of 1 over x minus 1 squared looks like. Look at the behavior of the function near x equals 1. Here for 1 over x minus 1, you see the function goes to positive infinity as x approaches 1 from the right, and the function approaches negative infinity as x approaches 1 from the left. But for 1 over x minus 1 squared, the function goes to positive infinity, which shouldn't be a surprise because 1 over x minus 1 squared is going to be always a positive number, never negative because of that squaring action. Now 1 over x minus 1 cubed, here's what the graph looks like. And again, you'll see that, from one direction the function goes to positive infinity and the other direction goes to negative infinity. And here's the graph of 1 over x minus 1 to the 4th. Of course, it has similar behavior as 1 over x minus 1 squared. So what does that tell you about what the power on that term in the denominator, but what that'll do for the behavior of the function near that 0 for the denominator? Okay, so I'll let you look at that real quick. Now let me just explain something here. When we were talking about limits earlier, now we are just only anecdotally talking about limits without actually formally introducing them to you in this course, at least at this point in the course. But when we talk about in the behavior of a function as x approaches some number, this is the notation that we're using. We're taking the limit as x approaches 1 of the function. Now, in particular, when you see this plus right here, this means that we're letting x approach 1 from the positive direction. Meaning, like for example, we're letting x approach 1 from this direction. So starting off with maybe x equals 3, then x equals 2, then x equals 1.5, 1 1/4, 1 1/8, 1 1/16, and so forth. But when we see limit as x approaches 1 from the left, that's what this notation means here. That means that we're letting x approach 1 by starting off with maybe x equals 0, then x equals 1/2, then maybe 3/4, and so forth. 15/16, 19/20, 99/100, and so forth, getting closer and closer to 1 for all numbers to the left of 1, for example. And all we're doing, folks, is we're just asking what's happening to the function as x approaches 1, either from the right or from the left. And it turns out that the function is going to infinity, either positive or negative infinity, depending, of course, what function and what direction that we're using. All right, moving along here, let's talk about horizontal or oblique asymptotes. Now, when you have a reduced rational function and it's proper, what does that mean? Well, you know what a proper fraction is. A proper fraction is a fraction where the numerator is smaller than the denominator. Well, a rational function is proper when the numerator is a smaller degree polynomial than the denominator. And for large values of x, for a proper rational function, for the higher degree polynomial in the denominator is going to go to infinity faster than the numerator because of the higher degree term. So the end behavior for proper rational functions is that the function will tend towards 0 as x goes to positive and negative infinity. So that means that the line y equals 0, which is the x-axis, will be the horizontal asymptote for the function. Here's an example of what we were just talking about here. Here's x minus 12 over 4x squared plus x plus 1. This is a proper function because the denominator is a higher degree polynomial than the numerator. So as x becomes larger and larger, the numerator is going to approach infinity slower than the denominator. So for large values of x, as x becomes large, the denominator is going to overwhelm the numerator. And of course, in a fraction, when you hold the numerator constant and let the denominator get large, then the whole fraction is going to get small. So we could tell from that discussion from the previous slide that the x-axis is going to be the horizontal asymptote for the graph of this function here, because it's a proper rational function. Now, if your rational function is improper, then we can divide the numerator by the denominator and then write it as a quotient with a remainder, with that remainder written over the denominator here, just like we would do with normal fractions. So there's a couple different ways that your rational function could be improper. It could be that the numerator and denominator are the same degree, in which case when you do the division, then the quotient's just going to be a constant. In which case, when you let x go to infinity or negative infinity, the function will approach y equals whatever b is, b being the result of the division. You'd have a horizontal asymptote. And again, that's when the numerator and denominator were actually the same degree. Now, it could be that the numerator was a polynomial 1 degree higher than the denominator, in which case, when you do the division, then f of x will just be some linear equation. In which case, when the function approaches infinity in the positive or negative sense for large values of x, and I should say for large magnitude values of x, then the function will approach infinity along a line when you're looking at the graph. So the graph will approach infinity either in the negative or positive sense along the graph of this line, linear function. Now, when the numerator is 2 or more degrees higher than the denominator, then the function's going to go either to negative or positive infinity along the graph of whatever the resulting thing. So it could be you have x squared plus something here. Well, the graph will go to infinity along the graph of that parabola, for example. So let's do an example here. Suppose that we've got 3 times x to the 4th minus x squared over x cubed minus x squared plus 1. Let's go ahead and do the division. Take the numerator, divide it by the denominator. You're going to be expected to do this yourself. But the quotient is 3x plus 3 with the remainder of 2x squared minus 3x minus 2. So here is the result of doing the division. Now notice that this part right here is a proper rational function. So when x becomes large, this whole fraction right here will go to 0. And that the graph of this function h will go to infinity along the line 3x plus 3. The 3x plus 3 would be the equation of your oblique asymptote. Okay, so 3x plus 3. So that's how you get the equation of your oblique asymptote. Let's do another example here. Suppose that we've got this rational function, 8x squared minus x plus 2 divided by 4x squared minus 1. Do the division, take the numerator, divide it by the denominator, and the result is 2 plus this remainder here, negative x plus 4. So here's how you can write that quotient with remainder. And then you notice that as x becomes large, this whole fraction will get closer and closer to 0, leaving you just with 2. So the function will approach 2. We can just go back to this equation, to this function here, and you notice that numerator and denominator are same degree polynomials, so you just take the quotient of the coefficients. 8 divided by 4 is 2. That right there could tell you, when you do that little mental division here, that's going to tell you the value, the constant value of your horizontal asymptote for this function here. The graph will approach the line y equals 2 as the horizontal asymptote of the graph. So as x approaches negative or positive infinity, the graph of the function will approach the horizontal line y equals 2. So y equals 2 is the horizontal asymptote of the graph. Let's do yet another example here. We've got this improper rational function. Let's go ahead and do the division. When we do the division, the result is 2x squared minus 1 plus this remainder over x cubed minus 1. So here's what the result of the division is. So for large values of x, of course, this proper rational function will go to 0. And then the graph of our function g will go to infinity, kind of along this parabolic path given by the graph of 2x squared minus 1. Okay. So for large values of x, the function will behave like this function right here, for large magnitude values of x. So this page right here just gives us a summary of what we have just talked about in finding asymptotes. Finding horizontal asymptotes or oblique asymptotes just by basically, look, if you have an improper rational function, just take the numerator and divide it by the denominator, and the results will tell you what sort of asymptote that you have. Unless you have a proper rational function, in which case the x-axis will be the horizontal asymptote. Okay? So that is it for today, and we have more to talk about for rational functions tomorrow. Okay? Don't forget you have the Chapter 4 quiz that I saw earlier. There was only one person who have completed. I've got most people's exams back, but there are still some people who I haven't got their exams back, so I'm going to have to hunt those people down. And there have been some people enrolled in the class, they haven't even contacted me regarding taking the exam, so I don't know how that's going to work out. So we'll talk about it later. If you have any questions about or issues about anything, send me an email and I'll get back to you, okay? All right, talk to you later. Take care.